Valmera and I are excited to introduce EOSS MMRM version 1.0 in this video. This is a R-Shiny application that is both light and versatile for estimand-oriented sample size and power simulations using MMRM modeling, which stands for Mixed Models for Repeated Measures. I'm going to focus on the background information, going over the definitions of estimands and intercurrent events, and some common strategies that are used to handle different intercurrent events. And then Valmera will take over the later half, giving an overview of the application and demonstrating how to use the application with a few practical examples. So first of all, what is the motivation for this project? The ICH E9R1 addendum on estimates and sensitivity analysis in clinical trials was finalized in November 2019 and has been subsequently adopted by many regulatory agencies, including the FDA. However, on the other hand, sample size and power calculation as a critical component of trial design has not been fully updated to align with the chosen estimates and intercurrent event strategies that reflect the trial objectives. Therefore, we have developed this tool to help the study sponsors to better understand the characteristics of the trial, particularly on the impact of chosen estimates and associated intercurrent event strategies on sample size and study power prior to the execution of the trial. The ICH E9R1 addendum, as shown on the left, has defined an estimand as the precise definition of the treatment effect reflecting the clinical question posed by a particular trial objective. A short and sweet way to say it is, what do you want to estimate? Or what is it to be estimated? When constructing an estimand, the study sponsors need to consider 5 key attributes: the treatment, the population, the variable or endpoint, the population level summary, and the strategies to handle the intercurrent events. The intercurrent events are defined as events occurring after treatment initiation that either preclude the observation of the variable or affect the interpretation of the trial results. Common examples of intercurrent events include premature treatment discontinuation, use of rescue medicine, and initiation of alternative therapy, among others. The ICH E9R1 addendum recommends various strategies to account for different types of intercurrent events. These strategies, as shown on the right side of the slide, include treatment policy, hypothetical strategy, composite strategy, principal stratum, and while-long treatment strategy. This shiny application we're introducing today focuses on the intercurrent event of treatment discontinuation and the intercurrent event strategies of treatment policy and hypothetical strategy. We all know that treatment discontinuation is a very common intercurrent event across all types of clinical trials. As for treatment policy and hypothetical strategy, they are also very commonly used intercurrent event strategies, especially in neuroscience clinical trials. Under the context of treatment discontinuation, treatment policy is defined as the pharmacological effect of the study drug for the pre-specified treatment period, regardless of treatment adherence. Hypothetical strategy is defined as the pharmacological effect of the study drug, assuming the continuation of randomized treatment for the pre-specified treatment period. In practice, under treatment policy, the study subjects are followed for efficacy assessments after discontinuing study treatment, and the values for the variable of interest are used regardless of treatment adherence. Under hypothetical strategy, however, the study subjects do not need to be followed for efficacy assessment after discontinuing the study treatment. We'll use the next couple of slides to illustrate the operational details of these two strategies. Now here, imagine that we have a trial with a continuous primary endpoint variable, which is measured at 3 time points, and the primary analysis is conducted with MMRM. The top section illustrates a subject who has completed the treatment course. The middle section illustrates an ET subject, which stands for an early terminated subject, who has discontinued treatment prior to post-baseline visit 1. And the bottom section illustrates another ET subject, who has discontinued treatment between post-baseline visit 1 and post-baseline visit 2. The blue arrow indicates the length of treatment period that is actually completed in each scenario. Now, for simplicity, let's just focus on the bottom section. Under treatment policy, we would bring back this ET subject after the treatment discontinuation for an efficacy follow-up visit. The efficacy observed at this visit is off treatment, and it's reasonable for us to believe that it is only a fraction of the full efficacy you would have otherwise observed if the subject had completed the treatment. In practice, however, patients often do not show up for efficacy follow-up visits when they are off drug, creating missing data. These missing data will be handled by MMRM with a mechanism known as implicit imputation, assuming missing at random. Now, this next slide shows a similar trial setup, but under hypothetical strategy, looking at both the middle and the bottom sections. The early terminated subjects are not required for coming back to complete the efficacy follow-up visits, thus creating more missing data compared to the operations under treatment policy. Again, these missing data will be handled using MMRM by implicit imputation. Because of this feature of hypothetical strategy and the missing at random assumption of MMRM modeling, trials using hypothetical strategy as their primary intercurrent event strategy often need to come up with more stringent sensitivity analyses to support the robustness of the trial results. Therefore, in order to help study sponsors better understand the impact of chosen estimates and the intercurrent event strategies on sample size and study power, we need the application to be able to accommodate trials that use MMRM as their primary analysis and accommodate both treatment policy and hypothetical strategy. Also, we want the application to allow for the specification of missing data pattern and extent, and allow for the specification of expected efficacy at efficacy follow-up visits under treatment policy. And finally, we also need the application to include placebo-like imputation for missing data under hypothetical strategy. Now I'm handing over to Valmira for the demonstration.
Thank you, Jean. In order for us to explore the app later, first we need to know how to access it. The files required to generate the app are listed in the link below. Please follow carefully the README instructions for running the code using RStudio. Use the app. The home page will appear when the app is run in R. Here, we provide detailed descriptions of input variables and stepwise directions to specify the simulation parameters in the user inference contained in the Shiny app page. In step 1, we set a random seed. In step 2, enter the number of simulations. A number between 5,000 and 10,000 is recommended to obtain stable simulation results. In step 3, enter the two-sided significant level. In step 4, enter the total sample size of each trial data. This is the total number of subjects planned to be randomized. In the step 5, enter the label TRT rate, enter 0.5 if your studies plan to have a one-to-one treatment allocation, a 0.67 if the treatment versus placebo ratio is 2:1, and 3:1 you would use a 0.75, and so on. Choose the number of post-baseline visits. Currently, the app set up into handling 2 or 3 post-baseline visits. Enter the baseline visit, common standard deviation, correlation among visits. For each of the post-baseline visits, efficacy is the expected difference between the treatment and the placebo arms for subjects who have stayed on the study treatment until that visit. EFU efficacy is the expected difference between the treatment and the placebo arms for the ET subjects who have been assessed for efficacy at EFU visits. Specify the ET rate. Click the simulation button to generate trial data and initiate the power calculations. A user can also browse the simulated data for the first simulated trial. Next, we illustrate how to adjust the simulation setup to specify for the clinical trials that handle ICEs using treatment policy or hypothetical strategy with 3 numerical examples. The examples are based on a conceptual clinical trial that employs a change from baseline in a continuous variable as the primary endpoint and uses MMRM modeling as the primary analysis. The trial assessed the primary endpoint at post-baseline visit 1 and post-baseline visit 2. We assume that the subjects randomized to the treatment arm are as twice likely to discontinue treatment compared to those in the placebo arm. We also assume that the full efficacy is a 4-point difference between the treatment and the placebo at efficacy 1 and 6-point difference at efficacy 2. Other common simulation parameters among these examples are described as below. Firstly, we would set up the random seed to the default mode of 1, 2, 3, 4. We would use 5,000 simulations. We will have the significant level of two-sided 0.05 and also use 2 post-baseline visits. Other parameters that need to be adjusted for the first example use a total sample size of 100. We would use a treatment allocation rate of 0.5, have a baseline visit to 38, common standard deviation to the default of 10.5, and a correlation of 0.5 among visits. In the example 1, we will illustrate the simulation of the clinical trials that actually handles the ICEs using the treatment policy. First, we assume that 50% of the ET subject would provide efficacy data at EFU visit 1 and EFU visit 2. And only 50% of the full efficacy would be observed at these EFU visits. So that means that EFU efficacy 1 has to be half of EFU efficacy 1, and EFU efficacy 2 has to be set up to half of EFU efficacy 2, 6. Next, we also assume that for the 50% of the ET subjects that don't provide efficacy data at the EFU visits, the MMRM model is actually going to impute by assuming missing at random. And to set up this numerical example, we would assume that the overall study dropout is equal to 30%. And we would assume that in the TRT rate 1, 20% of subjects will discontinue from baseline to post-baseline visit 1, and 10 into the placebo arm. So move it all the way to 0.1. In addition, we will also assume that 20% subject based off of the early enrollment will discontinue between post-baseline visit 1 and post-baseline visit 2, and 10 into the placebo. As mentioned earlier, we assume the 50% ET rate would provide efficacy setup, hence we move the cursors to 0.5. Now we are ready to simulate the data. The power obtained is 73.2%. Moving on to the example number 2, which illustrates the simulation of clinical trials that handle ICEs using the hypothetical strategy, assuming that none of the ET subjects who discontinue treatment before post-baseline visit 1 would provide efficacy data at EFU visit 1 and 2, and none of these ET patients who discontinue treatment between post-baseline 1 and post-baseline visit 2 would provide efficacy data at EFU visit 2. Next, the model will handle all the missing data implicitly, but by assuming missing at random. And the setup of the app for this situation is moving the cursor to 0 because no EFU assessment obtained, and therefore we obtain no treatment effect from EFU visits. Keeping the rest the same, simulating, the power got updated to 75.6 via this example. In the third example is actually a continuation of example 2, which considers the simulation for hypothetical strategy with placebo-like imputation for missing data. The sponsor may be interested in knowing the study power achieved when some proportion or all of the missing data are imputed into a placebo-like value, which is a common practice for sensitivity analyses. In this case, the user can set up the EFU rate to the proportion of the placebo-like imputation intended for the missing data, and then set the EFU efficacy to 0. In our situation, we will assume 50% of the subjects that have missing data will be imputed to placebo-like values for both post-baseline visits. Maintaining the rest of parameters the same, hitting the simulate button, the app generated a power of 57.78%. We actually explored different sample sizes, varying from 40 to 240, and we plotted the power obtained in each of the 3 numerical examples just performed into this graph. As shown in the figure, the hypothetical strategy in example 2 generates the largest power across the range of total sample size from 40 to 240, while the hypothetical strategy with the placebo-like imputation generates the smallest. With the hypothetical strategy, missing data are not explicitly imputed, but are handled with MMRM assuming missing at random. While the treatment policy, 50% efficacy is assumed for the 50% ET subjects who provide efficacy assessment at EFU visits, resulting in discounted overall effect size and smaller power, compared with the hypothetical strategy. Imputing half of the missing data by sampling from the baseline distribution, the hypothetical strategy with the placebo-like imputation reduces the efficacy of half of the ET subjects to 0 and has the most impact on power. In conclusion, this was an overview of EOSS MMRM version 1.0 and stepwise instructions on how to use the app with 3 numerical examples demonstrating the simulation setup for different ICE strategies. For study sponsors and researchers who are interested in more nuanced estimated-oriented power calculations, this app can be a versatile and easy-to-use tool that allows a specification of efficacy at EFU visits and missing data pattern. It can also combine different ICE strategies with missing data imputation and accommodates a more comprehensive understanding of the clinical trial characteristics under various scenarios. Thank you for your attention.